That way it's just a separate recording. So if you guys go search to find that on the YouTube channel, you're not having to watch 15 minutes of that and then our biomolecule chat. My goal is to make this as easy as possible. Okay. This popped up as still screen sharing, right? Okay, great. So, still no EpiPen. Almost everything on the first go. Who does this? I feel like someone must come in here and not know how to close it, so they just like swipe it as far into the corner as they can. That has to be what's happening there. All right. Well, good morning, everybody. So, thank you. So today, we are not going to keep talking through this thing. All right. We are going to pick up our conversation for the love of lipids. All right, so remember our big goal here is to compare lipids with our other biomolecules. I miss having a drink. So some of the things we talked about on Wednesday, okay? So we really focused on this hydrogen-carbon chain. So really noticing the lack of oxygen. So instead of being polar, okay, so having that selfish roommate that has that little bit of charge that allows it to bond and mix with water. By not having all those hydroxyl groups or all of those oxygens, okay, we see that all we have are carbons and hydrogens for all eternity. It's a desert. A desert, no oxygen, right? So we are non-polar. And remember, this was intuitive to us, right? If we picture pouring olive oil in water, it floats. Okay, so oil does not play well with water, and that's because we're lacking that selfish roommate that allows that electrical charge or that bonding component that our carbs have. Right? Remember, we pictured carbs. Carbs dissolve. Sugar dissolves in water. Okay? So that was one feature. The other feature we had was this carboxyl group. Right? So here we have the carbon double bonded to oxygen. Okay, so that's the carb part. And the oxyl. Okay, because we have the hydroxyl sticking off at the end. This was that first indication that we really needed to practice our terms. So we have the carboxyl group in lipids. Oh, heavens. But we have the what? What's this? Carbonyl. Good. Okay, so we still have that carbon bit. Okay, we have this boring H. Okay, they look very similar. They're spelled very similar. Okay, so some jerk or jerkess, okay, back in the 17 and 1800s, okay, did not do us any favors with the namings. So we really want to make sure we're practicing and recognizing this. So remember, this one was in our carbohydrate. Carbohydracious. That's some awful spelling right there. So carbonyl is in the carbohydrate. The carboxyl is in the lipid. Okay, in fact, this carboxyl group, whoops, A now, I said yellow, is the only space we're really seeing oxygen in our lipids. Okay, so for standard size of a molecule, we're getting very little oxygen. This is something else that's really unique as well. Okay, I think this is where we left off on Wednesday. Okay, So the other thing we want to note on here, okay, is what is the point of a lipid? We kind of mentioned this in passing, okay? And it's going to be several slides before we get all of this because we'll find there's a lot of surprising jobs that a lipid does. Okay, but from the start, it's pretty intuitive. When I think about lipids, I think about how delicious they are, right? Butters, oils, fats. Okay, so they're fuel and storage, right? Fat at its core is just energy storage mechanism. Okay, that also happens to be, for better or for worse, okay, a structural component in our bodies. Okay, love the skin you're in. Okay, so most of this was review, but I was worried that we kind of rushed through it a little bit on Wednesday, so I wanted to make sure we got to back up. Does this all feel pretty good? As it is, and in comparison to the structures that we saw in carbohydrates Monday/Wednesday. Okay, so here's the key when we're thinking about lipids. So this is sort of a base lipid. Okay? When I'm looking at this, this is the kind of lipid that you actually would see in a stick of butter. Okay, but as I mentioned, there actually are some unique lipids. Why am I carrying that around? Okay, there are some unique lipids that are doing more interesting jobs. Okay, so the first thing we want to pay attention to is how exactly are we putting together a lipid to get some variety here. And while this looks daunting, okay, we're going to find really quick this is actually some old hat. Okay, so, okay, as we look here, all we have in these middle colored boxes, okay, right here, okay, are the same fats that we have on the last page. Okay. Up here, we have what's called an alcohol. Okay, so this is just something that's long and has some very familiar structures on them, right? So one big structure that has 3 hydroxyls on it. We know what hydroxyls are good for, right? So if we're going to create a large molecule from several small molecules, are we going to use hydrolysis or dehydration synthesis? For creating something, which one are we using? Dehydration synthesis. Good. Okay. And despite its daunting look, dehydration synthesis works here exactly the same way as it did with our sugars. Okay, we're just doing it 3 times all at once. All right? Erase my swoops here. All right, so let's just look at our top one. All right, it's easier to look at one. Okay, so we have 2, 2 hydroxyls. We know we need hydroxyls in order to do dehydration synthesis. Okay, we know our goal is to dehydrate or to lose a water molecule, right? Okay, so, okay, as my line's already indicating, I'm going to take 1H, 2H, okay, so that's those, and an oxygen. Okay, so there goes my water. Okay, That's exactly the same as before. I haven't done anything new. Okay, what's that leave me? One oxygen, right? Let's get a different color here. Okay, that's the same as before too. So if I look at my final product, there's my final oxygen. So I have my final compound holding hands over an oxygen. Okay, so it looks really intimidating. Okay, because we're doing a whole bunch of stuff all at once, right? We're doing this 3 times, which is why we get 3 waters. Okay, but the process is exactly the same. We're just going to go in, we're going to use these hydroxyl groups sticking out at the end, okay, like little miniature Jane and Carls. Okay, does everybody see that? What we've done here? Okay, we're ignoring this bottom box now. I'm going to address that in a second. Does everybody see how we've created our new bond? Is there any questions about that? Okay. So the key here, the only thing that's really different, aside from the fact that we've done it 3 at once, is we're naming this a little differently. And this is what this bottom box is talking about. So remember when we did sugars, we called them covalent bonds, right? Because those were just boring C to O to C bonds, right? And if you flip back in your notes, there wasn't anything else attached to those carbons, right? They were pretty boring molecules otherwise. On these guys, they're called ester bonds. You can blame the chemist for this one. Okay. They're called ester bonds because on this side, we do have some interesting business, right? So on the one side, we didn't just use a plain boring hydroxyl group, right? Technically, we used a carboxyl group. Now, at its fundamental core, we were only using the hydroxyl part. So it's the same, okay, but the resulting bond is to this. All right? And so that's what makes it an ester bond instead of a covalent bond. Okay? Doesn't change our process. Okay? Doesn't change the functionality of the final product. Right? Ultimately, right, you just have 2 selfish roommates and it does a whole bunch of electron sharing stuff that we do not care about because this is not chemistry. Okay? So for all we care about, it just is a different name. Okay, but that's why it has a different name, because we've introduced another selfish roommate. Right. Does that also make sense? Okay, so this is the key when I said really learning hydrolysis and dehydration synthesis is important, because here we are again in lipids, pointing at the screen, right, doing the same thing again. Okay, we've added a little dramatic flair to it. I don't want my own name. Okay, but ultimately we haven't done anything different than we did in the vocabulary intro or that we did with carbohydrates. Okay, we just added a hat. Any questions online, Jasmine? Okay, any questions about this? Okay. So the key here is using dehydration synthesis, we can make any shape of lipid that we want to. And there are two very specific shapes of lipids that have some very important jobs. Okay, so in addition to fuel, there's one type of lipid that does a very specific and important structure job. And that's called a phospholipid. Okay, arguably one of the most important compounds in all of your cells. Okay, so let's take this in piece. Well, I'm going to do that wrong. We want this technically here. Okay, if we look below the green line, that's actually the lipids that we've made up to this point. Okay. There's our C double bonded O, right? This would have been the hydroxyl group. All right, so here's our alcohol. Okay, so this is all the stuff that we made. Okay, this is where dehydration and synthesis happened on the last screen. Okay, and remember, when we have these kinks or bends on a molecule, this is some lazy chemist business. So what goes at those corners? What did we say on Wednesday? What goes at a corner that isn't showing anything? Carbons. Good. Excellent. These are all carbons. Lazy chemistry carbons. Okay, so these are our hydrocarbon tails. Okay, the long deserts that we were talking about. Okay, so this is familiar looking on the bottom half here. We've just sort of like turned it vertical and adjusted the way we've drawn it. Does everybody see that? Or we're just going to ignore that top bit right now. That part is new. But all this bottom stuff is old. Okay, we're just changing the way we're drawing it, and we've turned it. Okay, so this is exactly like the last slide. We've just rotated it vertically. We've tipped it 90 degrees to the right. Everybody see that? Okay. There's too much on here, so I'm going to take all that away. All right. So, this is where we're getting, I'm going to recut this now. If we look at this bottom part then, okay, we already knew that this was hydrophobic, right? We called this the desert for a reason. So we know there were no oxygens here. I remember being oxygen-free. Okay, makes you nonpolar. Okay, what does the term hydrophobic mean? Does anybody remember what the definition of that is? Water-fearing. Good. Okay, so this is why stuff floats on water, right? This is why those oils float on water. It was basically just this. Okay, now this compound is different though, right? Because we've got a big chonker on top now. So in addition to having those teeny carboxyl groups doing their business, we have something brand new now. Okay, the phosphate group. Okay, this is big and uniquely has an awful lot of oxygen. Okay, per space now, it's got 4 oxygen to its one little element. Right, so we have more than doubled the amount of oxygen. And importantly, okay, it's all isolated, right? So we've added a whole bunch, okay, and they're all up here. So we have this nice little pocket of oxygen, kind of all clumped together, hanging out in the corner. Little clip of oxygen. Okay, so oxygen are polar. Okay, these are our crappy roommates, right? So if we have a whole bunch of oxygen hanging out in one area, that makes them hydrophilic. What does being hydrophilic mean? Mixes with water. Good. All right, literally water loving. Okay, so wait a minute, this just got weird, right? So now we have a compound that is half and half. Okay, half hydrophilic and half hydrophobic. Okay, this sets up phospholipids to do something absolutely amazing. Okay. If we take the polar hydrophilic, or could spell philic, I feel like it should have two L's, and I don't think it does, heads, okay, and point them all in one direction. Hydrophobic tails, as their name implies, phobic, right, phobia, fearing, they're scaredy cats. Okay, they don't like playing with water. Okay? They don't like playing well with others. So all the hydrophobic tails sort of get together and tuck themselves together in a closet. Okay, so they all face each other. I'm afraid. Okay, sticking on either end, the polar heads out. And the polar heads don't mind being out because they're hydrophilic. They do play well with others, right? So what we end up creating here is your plasma membrane or your cell membrane. Okay? It's basically like a mini protective wall. So on this side would be sort of like outside the cell, where it's all wet and sloshy, gross and dangerous. Okay? This side, just gonna make a little asterisk because I can't write over there, would be inside the cell. And that's also wet, right? Because we know that the cell is filled with things like the cytoplasm, which is a liquid. So our polar heads, our water-loving polar heads, are happy touching all of this weird wet stuff. And the non-polar tails create a protective barrier that water doesn't cross well. That looks like crap, doesn't it? Okay, so we'll end up talking about this a lot when we go into the cell. Okay, but the key here by having this do not cross space, okay, is things can't cross easy. Okay, water can't cross it, dangerous things can't cross it, right? The cell has to have a special way to get things it wants across, like food, okay? But just anything can't get across, okay? So this creates that bag that holds the cell together, okay? And all because it has this half and half system, okay? The scaredy cat butt, okay, and the tough plays well with others head half. Which is pretty mind-blowingly amazing if you ask me. Okay, so we'll spend a lot of time talking about the cell membrane in general, but does this make sense how phospholipids, okay, so a lipid with a phosphate head, phospholipid, how that's put together and how it's valuable? Okay, so this is another specialized structure that lipids can do.
So there was a question in the chat,
Okay.
and they asked, so isn't this called a selectively permeable membrane?
It is. They're correct. So another term for this is selectively permeable membrane. And we will talk about that more when we get to cells. And that's because it is going to allow things like food across, but it's going to do that via protein channels. They aren't going to go through this itself. Okay, the only thing that's really going to get through here are really small molecules like oxygen. Great question and great term. Okay, any other questions, either in seat or online? We good? All right, great job, guys. Okay, so there's one last lipid that I want to talk about. Okay, the fact that lipids in general are really lacking this oxygen is really key to their functionality. And so if we look at, let's not use black because it doesn't show up well. All of the images that I have on the screen for you, these are all also lipids. Okay, and this is the first time that I'm showing you lipids that are ring structures as opposed to chain structures. Okay, but we still are going to know that they're lipids because if I look at the structure, the key feature here is we're still lacking a lot of those oxygens, right? So remember, all right, I'm going to look at this one first as sort of the general example. When I'm looking at all those kinks in those bends, right, remember the kinks in the bends are all carbons, okay? So every kink and bend is a carbon. Pew, 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 pew. You must add them with sound effects. Okay, so that's our basis when we're looking at the rest of these. So when I'm looking at the rest of my structures, if I were to say on a test, is this a lipid, is this a protein, is this a carbohydrate? So I need to pick now, right? This is something you'll have to do. So if I was looking at estradiol, I would want to say, okay, I know, for example, the presence of hydroxyl groups. Okay, so remember hydroxyl. Is one way that I know something is a carb. Right, that's the one we've really spent the most time on so far. Okay, now estradiol has some hydroxyl groups, right? Got two. Okay, but it's a pretty big structure. Okay, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 carbons and 2 hydroxides. Okay. If you guys flip back and look at the and let's look at the carbohydrates that we had before. So let's look at fructose. We have 1, 2, 3, 4, oop, 8, let me draw. 4 carbons, oops, 5 carbons, my bad. I can count today. And 1, 2, 3, 4, 5, 8, 5 hydroxides. Okay, so even though the total number of hydroxides isn't high, we have a lot of hydroxides per the number of carbons, right? And so this is really key here. Okay, what we want to be able to say is, if it's going to be a carbohydrate, okay, we should have almost as many hydroxides as we do carbons on a structure, right? In other words, you should have a lot of hydroxides dispersed across your entire structure. I'm going to erase this again because this is going to get confusing when we flip back. Okay. This does not seem to be the case for estradiol, right? We have some hydroxides, but they are rare and limited. Okay, they aren't clumped together. Okay, they are few and far between. 2 for 17 carbons is not a lot. Okay, even the ones with most, 1, 2, and then we could even say 4 oxygen. Ooh, 5. Man, I can't count today, can I, guys? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 to 20 carbon. Okay. So we can say pretty strongly that these are lipids, okay? Because there's just not enough oxygen on here. There's so few oxygens. This is really falling into that category of having huge deserts, right? Large sections of those hydrocarbons where there's no oxygen present. Even though we've looped them up, right, into rings, we can still see them, right? Swaths of deserts where there's no oxygen. Everybody see that? Okay. Now, these swaths of deserts are really important. Okay? So these are all, if you haven't recognized them yet, testosterone, estrogen. Okay, these are all steroids. Okay? In other words, these are type of hormones that travel through your body as messengers. All of steroids are a form of lipids. And this is really important if you think about the function of a steroid. Okay? So why, if your body was going to try to send a message from a gland in your brain, okay, to your pelvis, would it not use a carbohydrate? What would be the problem if it sent that as a carb in your blood? It would dissolve, right? Right? Because carbs are sugar. If you send a carb-like messenger in your blood, that's going to dissolve in like 10 seconds. That is not a very valuable messenger, right? So all of the steroids or messengers that your bodies use are lipids, because lipids will not dissolve in your blood and so will make it to their intended target. And that's a really valuable system. Okay, so sort of a surprise function of steroids or of lipids is as messengers for cells. Okay. We'll stop there. We will start on Monday with our participation review activity, so I don't want to have to rush through that. So be prepared. You can even start thinking about that before we come back. Your Socrative should be up. Guys, I cannot tell you how important the Socrative is. I know I sent an email about it, but some of you are still forgetting to do it. If you don't do it, it's hard for me to know if you've been in class or not. Right? I'm learning some of your names. I still don't know all of you. And boy, the masks do make it hard, right? Particularly too if you're online because you're not turning on your faces. That's making it hard too. So do make sure you fill it out. And as you've noted too, we actually are reading the exit tickets because we're incorporating that stuff. So it is important. So I do care what you say. Y'all are important to me. So please make sure that you fill it out.
So really quick, there was a really good question in the chat, and they asked, will they have to memorize all of these steroid structures?
So absolutely not. So the question is, do you need to memorize any structures? And the answer is no. So what I want you to focus on is what is important to recognize a structure as a lipid or as a carb, but you would not need to know, for example, testosterone versus estradiol. Good question. Okay, back 2 rows as usual. When you guys are finished up, you're welcome to go. Great job this week, guys. You can stop recording too.